Hello everyone and welcome to another Stat 437 lecture video. In today's video we are going to be talking about continuous time survival analysis. So over the past few videos we had looked at discrete time survival analysis and how we can use non-parametric methods in the discrete time case, as well as how we can sort of take a likelihood approach, which gives us this nice way of formulating the problem through GLMs. So now that we're done with the discrete time data, we're going to take a look at the continuous time data. Most survival analysis that you're going to see, most of the methods that people use for survival analysis will assume continuous time. And that's because, generally speaking, continuous time distributions are nicer to work with. And there's quite a few sort of nice ways that you're going to be able to sort out the time to event data in the continuous time case. So today what I want to do is introduce you to sort of the overarching concepts that we're going to be dealing with for the continuous time case. We're going to see a little bit how it's going to differ. We're going to sort of try and situate ourselves within this parametric framework for the continuous time. And then over the coming videos, we'll explore in more depth all of the ideas that we're talking about here today. So as always, if you have any questions about anything we talk about, please reach out and let me know. And otherwise, we can get started here talking about continuous time to event data. So I want to start by introducing sort of an interesting example to keep in mind. And that's this idea of the timing of someone's first marriage, right? So it's a problem that can be framed through the lens of survival analysis, right? Because if you say first marriage is the event that we care about, then we could look at how long does it take until a person's first marriage, and this can be just set up in the same sort of framework that we've been working with. Now, of course, if you're measuring time in years, we can take a look at the survival analysis through discrete time situation, right? We could do that. I think the timing of the first marriage is an interesting example that sort of spans both possible considerations. And why do I say this? Well, there are people who get married fairly young, right? Say, in their late teens or early 20s. And then there are people whose first marriage won't happen until, very late into their lives, say, into their 50s or 60s, right? And so if you want to fit a discrete time model to this, you're sort of looking at, say, a 40-year period of possible outcomes. And of course, you can fit a discrete time distribution with 40 different bins, but you're starting to, think about, you have 40 different estimates for the different hazards. You have to think about, fitting logistic regression models that are going to have 40 factor variables before you've included any of the covariates. And so we're sitting at this edge here where it certainly could be a discrete time problem, but we could also think about this as just treating age as sort of a continuous variant, right? And you see this a lot in statistics, but I think it's important to point out that while you can always treat variables as discrete, there's sort of this subject matter judgment that we want to make. And oftentimes what we're going to have are problems that, would be discrete, except they span too wide of a range and it's easier to treat them as continuous in that way, right? And there's also this point that, of course, we could measure the time of your first marriage a little bit more precisely, right? We could measure it down to whatever sort of fraction of a year we care about. And so on some scale, we could treat it continuously in that way as well. But, just something to keep in mind there. So recall from our earlier lectures that in the continuous time setting, we have our CDF. You're used to working with that. We have our PDF, which is the first derivative of the CDF. Again, you should be used to working with that. We have the survivor function, which is 1 minus the CDF, right? Exactly the same way that it was in the discrete time case. And then we have our hazard function. And the hazard function is interpreted in a similar way as it was in the discrete time case, but because we're dealing with continuous variables here, it's no longer a simple probability statement. So instead, we sort of use this limit definition, right? Where we're saying it's the limit that t falls into some shrinking interval, assuming that t is at least the time now. So it's a similar idea, but it's like how a density is not a one-to-one mapping on with the PMF, right? And in the continuous time case, these all uniquely define the distributions, okay? And so um, with that, we can sort of, any one of these is going to be good enough to characterize what's happening with our random variable t. We also define, for convenience, this cumulative hazard function, right? And all this is it's the integral from 0 up to time t of our hazard function. And the reason that we do this is because there's this nice relationship between the cumulative hazard and our survivor function, where the survivor function is equal to e to the power of the negative cumulative hazard. Okay, so that's just sort of a notational convenience there. So given sort of everything that we have here, the approach that we're generally going to be using is this likelihood approach in the continuous time case. There are non-parametric methods that don't rely on likelihood, and there are non-parametric methods that stem from a non-parametric likelihood, but we're going to sort of rely on parametric likelihood approaches to survival analysis. And so we have to sort of think about all of the same types of hurdles that we've been dealing with this whole time, right? So primarily this means censoring. In order to account for censoring in general, we need to jointly model the distribution of Ti and Ci, right? Ci being our censoring time, Ti being our event time. And we had talked about how there are different mechanisms for censoring. Sometimes it's going to be deterministic, at which point it doesn't have an interesting model. We would just know it's at some fixed time, but it could also be random, right? And so as a general rule, we have to do this joint modeling procedure. But joint modeling procedures are not particularly fun to have to do, and moreover, we're not generally interested in the censoring mechanism. We don't normally care about why someone has left our sample. We just need to take account of the fact that maybe they did in order to get productive estimates for the event process, right? And so what we're going to be doing is we have all of this notation that's built up around this. So we have our density for the event process, which is going to be given by f, and we're going to parameterize it with theta. And then we'll define a similar density for the censoring process, right? Because you can think about the censoring process as basically a time to event process itself, right? It's the time until someone gets censored. And so all of the same quantities that exist for the event process are going to also exist for the censoring process. It's just not a process that's particularly interesting. But so we can define the densities there. We're going to let sort of this t tilde notation be the notation for the observed time, right? And that's going to be the minimum of someone's event time and their censoring time. Before we saw that as an x, but we need to keep x around to allow for covariate introduction, right? So we're going to use this t tilde. And this delta I that we have here is going to be an event indicator. So delta I is going to be a 1 if we observe the event, and it's going to be a 0 if we observe them being censored. Now we're also going to introduce this fancy G notation here, and that's the survival curve for the censoring distribution. Okay, so it sort of corresponds to S, the S that we've been thinking about for T, except it's the survival curve for our censoring process. And so now we start introducing assumptions that are going to let us simplify, right? So as a general rule, just taking these above points here, we would want to sort of model out the joint distribution, and you're going to need to specify everything. But if we're willing to assume that censoring is independent, right? So if we can assume that Ti and Ci are unrelated to each other, well, now suddenly we can actually just exploit the individual densities and the individual survival curves. Okay, and how do we do this? Well, we would note that the likelihood contribution for an individual is going to be given by this expression here. And we can sort of break this down into two components, right? So this first component here deals with the event process. And what does this say? Well, if Ti is observed as an event time, right? So if the event occurs, then the likelihood contribution of an event occurring at time Ti is given by our density evaluated at that time, right? It's the same thing that we would be, thinking about with a normal likelihood, where you just take the density evaluated at your observed point in time. So that's going to be, if the individual has an event occurring, delta I is going to be 1, and this term is going to sort of turn on. If delta I is 0, right? So that we observe them being censored at time ti. Well, then what contribution do they have to the event process? All we know is that they observed at least as long. We observed them for at least that long. They survived at least that long. And so what we know is that the probability that they survive at least that long is the survivor function evaluated at the observed time, right? And so for the event process, you're either going to get a contribution equal to the density evaluated at our observed time, and that's if the event occurs, or you're going to get a contribution of the survivor function evaluated at the observed time if the event does not occur. We have a similar thing going on in reverse as the second set of terms over here, right? So if the individual is censored, right, so delta I is 0, well then what's the contribution to the censoring process? It's the density evaluated at that time, so it's this G term. And if the individual is not censored, then what do we know about their censoring? All we know is that it would have taken place after our current time, so we evaluate the survivor function at the observed time. Right? So you can think about this as this first component being the contribution to the event process, the second component being the contribution to the censoring process. And for every individual, you're going to only have two of these four terms here, right? You're either going to have the density of the event process alongside the survivor distribution of the censoring process, or you're going to have the survivor function for the event process alongside the density for the event process, or for the censoring process, sorry. Okay, and so hopefully that makes sense. You can sort of think about that as the two different cases, right? Whether someone's censored or not, and then we just combine them, collapse them using that notation. And if we will make the assumption that we were making in the discrete time case, that censoring is uninformative, so that this theta parameter that we have and this phi parameter that we have are completely unrelated with one another, well then we can just ignore the second component here, right? And so under the assumption of independent and uninformative censoring, our likelihood contribution simplifies to just that first piece, where you either get the density if the event's observed, or you get the survivor function if the individual was censored. Okay, so hopefully that makes some sense. But with this, we sort of have our full likelihood, and it's going to be based on our density and our survivor function. But if you recall, we have this nice relationship with our hazard function, right? So the hazard is equal to the ratio of the density to the survivor function. And so we can use that to actually rewrite the likelihood contribution to be equal to the hazard function should actually have an exponent on it here. I'll correct that in the slides, but we have this written in terms of our hazard function and our survivor function, okay? And so if we've specified some specific distribution, then we can actually work out this likelihood, because given a specific distribution, we know the form of the hazard, we know the form of the survivor function, and we can just use maximum likelihood in order to estimate this, okay? And yeah, to be clear, to clarify what I was saying here, there should be a delta I on this first term here, on this hazard function, okay? So that's the general likelihood procedure, right? We'll see that in some more detail afterwards, but there's going to be a certain set of functions, of distributions that we typically want to work with. All right, so to briefly refresh, let's talk about location scale families for a moment here. If we have a random variable y, if you can write y in this form, so y equals a plus bx, where x and y come from the same distribution, then we say that this distribution is a location scale family, okay? And so what are we saying here? Well, if you think about y as being normally distributed, right, then if you take a to be the mean of y, sorry for this bad writing, but just to clarify, and b to be the standard deviation of y, and then x is a standard normal, right, then we can write any normal distribution as its mean plus its standard deviation times by the standard normal, right? So the normal distribution is a location scale family. And any distribution that can be broken down into this form is called a location scale family. And the reason that we like these is because they're quite convenient, right? We can multiply them and we can shift them around, and that doesn't change which family we are working with. So the example that I was just walking through, right? If you take x to be standard normal and y is a normal with mean mu and variance sigma squared, then y is equal in distribution to this expression, mu plus sigma times x, right? But we could also do this with something like the exponential distribution. Not directly, the exponential distribution is not directly a location scale, but if we take the log of the exponential distribution, then it actually has this form of log rho, where rho is the rate parameter, plus w, and w is going to have this extreme value distribution. And so the log of an exponential distribution actually turns out to also be a location scale family. Okay, so why do we care about this? Well, we can introduce this idea of location scale regression. So if you have a random variable and it's just some transformation of another random variable, say, if it looks like mu plus w, right, which is what we saw with that exponential distribution we were just looking at, right? If we take a log transform of an exponential distribution, then we get this log plus w. We have a mean plus some error term here. Then this looks like what we think about with a regression model, where we can treat w as some sort of error term that we don't really care about, and mu as the mean of the distribution that we do care about, right? And so this is exactly what we're doing with standard regression, right? And the standard regression model, I'll flip back again in the slides here. If you assume that your outcome is normally distributed, then you would have the mean that you care about plus some error term. And normally we would write that as epsilon, right? But it's just the mean plus some epsilon term here. And then we can break down the mean and actually, fit the mean based on different covariates. But so anytime that you have a location scale family, you can write it in this form that sort of looks like this regression model, right? And that's going to be super useful for us because if we can work with a location scale family, then we sort of get these nice regression models coming out of this. So the estimation for the distribution, for the part of the distribution that we care about, ends up being this estimation of mu, which again is exactly what we're doing inside of regression. And so, how does this help us? Well, I want you to think for a moment about the types of distributions that you're going to be able to use for survival analysis, right? So what are the requirements on the distribution of TI? We know that we're dealing with continuous distributions, and we know that TI has to be greater than or equal to 0, right? We can't have negative survival times. And so we're sort of forcing there to be this positive distribution. But then also there's going to be some practical considerations, right? Where the probability that TI is really large is definitely going to sort of have to trail off, right? You can't have something surviving forever. At least typically you're not going to have something surviving forever. And so normally you're going to see that there's this long tail of the distribution, but it trails off fairly quickly. And so when you start to think about, what does a distribution that might be appropriate for T look like, we start to really limit the families of distributions that we can actually work with. Now, what ends up being nice is that a lot of the families that we like to work with, like an exponential distribution, right? An exponential distribution fits all the parameters we had. It turns out if we take a transformation of them, oftentimes those are going to be in this location scale format. And because of that, we're going to be able to derive these really nice regression models for continuous time data. So what does that look like? Well, we're going to assume that we have independent censoring, right, which we did to get our likelihood simplified. We're also going to assume that there's non-informative censoring so that we don't care about that censoring process at all. And then we're going to specify a parametric form for the distribution. And I'm saying it's typically going to be a location scale family. We'll see a little bit in more detail after the fact, but really what we're going to say is it's going to be a distribution that we can transform into a location scale family. So the exponential works because if you take the log of the exponential, it's going to be location scale. Okay? And then we can just do maximum likelihood estimation. And it's sort of that simple, right? We have the form of our likelihood. If we have a parametric model, we can fit that. But the benefit to doing it in this way is that now we can start to specify some sort of model for that mean parameter, and we can start to see the effects of covariates and so on and so forth, right? So that's the general process, parametric estimation in the continuous time setting where we're allowing for censoring, okay? We're going to see this in a lot more detail when we look at the specific types of regression models, but this is the overarching idea that we're going to be working from. It's going to be directly based on maximum likelihood from these results that we've derived. Now, we've talked about this idea of censoring. We've accounted for censoring in this, but what we've not accounted for yet is the truncation, right? And we didn't really talk about this a lot in the discrete time case either. So let's, spend some time looking at what truncation is. So truncation occurs whenever your sample is biased based on containing only some subset of individuals. So if you only allow for individuals with their time being greater than some event, or alternatively, their time being less than some event for some threshold, then this is what we call truncation. So the standard example that I believe we've seen before in this class is if you think about trying to study the impacts of the radiation of the atomic bombs dropped during World War II, and you want to study the impact of that on the population that was affected. Though the bombs were dropped in 1945, and so if you think about it, we really weren't going to start studying that until at least sort of into the 50s. And so any individual who had such a severe effect of those bombs dropped that somewhere in the intervening 5 years they experienced whatever event you're trying to study, then you're not going to be able to include them in your sort of longitudinal study because of the fact that their event occurred before you started filming or before you started running your study. And so because of this, you have this threshold of U, which is some number of years after the event occurred. And unless someone survived at least that long, they're excluded from the study, right? So it's this form of sampling bias where in order to be included, you have to have operated in some interval. And the problem with truncation is that we end up needing to do a conditional analysis, okay? There is no way around truncation. With censoring, we can work around it. We don't need to condition on censored times. However, with truncation, it's a form of sample bias, and we need to change the point of inference. So what do I mean by this? Well, specifically, if we start taking a look at the likelihood, we actually need to use the likelihood to be based on this conditional density here. Okay, so it has to be conditional on t, for instance, being greater than u, or equivalently less than u if you were truncating on the upper end, right? And so if you have truncated data, you need to be working in the conditional analysis. Of course, we can write out this conditional distribution as the ratio of the marginal distribution over the survival distribution, right? And so you can work from it in a similar way. But there's no way around using a conditional analysis for truncated data. So that's sort of the high-level, fast run-through of what we're going to be doing with continuous time survival analysis. So we can use parametric likelihood analysis to fit models for the continuous time data, and that's what we're going to spend the rest of this course looking at. We reviewed what location scales families were, and I tried to motivate why we care about them, and that's because they present these really natural regression forms, but you're going to be seeing those a lot over the coming lectures, and so hopefully, seeing them a number of times will reinforce why we like them so much. And then we also talked about truncation, and truncation is a problem separate from censoring. Truncation is a problem because we need to do some conditional analysis. But later on, we're going to also see how truncation can be useful for us in fitting these models, right? So sometimes we will want to actually work with truncated data, but it's important to keep in mind that if your data are truncated, you need to perform conditional analyses. There's no way around that. We can use standard likelihood techniques, which is going to give us all of sort of the tooling that we like around likelihood, right? So long as our parametric models are specified nicely and correctly. And so I want to take just a brief moment to discuss what is going to come up next in this course. All right, so in the following lectures, we're going to dive into the sort of deep into the theory of this, right? So I ran through quickly how to motivate that likelihood today. We're going to talk in a lot more detail about that, where we'll actually work through the process of deriving that. We're also going to walk through some location scale families and show this implied log linear regression models that I've been talking about. So we'll see the exponential, and we'll see how that sort of comes out, and we're going to be working with those regression models that come out of that as well. And then we'll also do some actual model fitting of these likelihood models in R, okay? And then what we'll do is talk about sort of the two most common types of continuous time models for survival analysis. Now, they're both related to this whole process that we're talking about here, and so I'm trying to build into how you may have gone about discovering these models for yourself. But the sort of two most prevalent kinds, other than non-parametric, the two most prevalent types of parametric continuous time models are what we will finish off the course talking about. And so that's going to be the accelerated failure time models and the proportional hazards models. And both of those are related to what it is that we're doing here. They're both a form of regression model, and they're both quite useful. And so then we'll finish off the course by introducing what those models are conceptually, talk about a little bit of the theory, though by the time that we're getting there, most of the theory will already have worked through. And then, we'll see them in R and sort of explore them. And then that's going to be it for the new content covered in this course. So we're getting really close to the end here. Hopefully all of this made sense. Of course, if you have any questions at all, please reach out and ask me. And otherwise, I will see you all in the next lecture.